Hi everyone, this is Kalyan this side and welcome back to Chemistry Universe. With this video, we'll start the chemical properties of aldehydes and ketones. And as I mentioned in the beginning of the introduction of aldehydes and ketones, this is a pretty big lesson, got a lot of reactions. So I've broken them down into smaller pieces. So this one is about oxidation. We'll only talk about oxidation reactions. And I'll also show you some required videos which can be used as tests also. And so we will do oxidation here. In the next one, we'll do reduction, and slowly we'll do various types of reactions. So that each video can be kept as small as possible. So let's get the ball rolling. And this is the chemical properties of aldehydes and ketones. We start with oxidation reaction. All right, so let's look at some general nature to understand what kind of reactions aldehyde and ketones show, because we need to know that. Due to higher electronegativity of oxygen, the mobile pi electrons are pulled strongly towards oxygen, leaving the carbon atom deficient of electrons. So this carbonyl compound has a resonating structure, which is this one. Obviously, its contribution is going to be very small, but it does contribute. And this clearly shows that the carbon of a carbonyl compound has some kind of a positive charge, however small it may be, not only due to the inductive -I effect of oxygen, but also due to the resonance effect, the ability of the pi electron to move towards oxygen and make the carbon positive charge. This carbon is therefore electrophilic, meaning it would invite nucleophiles to attack on it. So the nucleophilic part of the adding molecule attacks the carbon, while the electrophilic part will attack the oxygen. Now the bond energy of the CO bond is very high. It's around 178 kcal per mole, which is greater than C double bond C, which is merely 146 kcal per mole. Now generally, aldehydes are more reactive than ketones towards nucleophiles, because in ketones what happens is, on both sides of the carbonyl group you will have groups which are alkyl groups, and these groups would these alkyl groups on either side would give a plus effect and make this carbon less positive, and therefore you will find that aldehydes are more reactive. Now the nucleophilic reactions of aldehydes and ketones depend on the size of the groups attached to the carbonyl carbon, the electronic effects of the groups. And the reactions of carbonyl compounds can be classified as oxidation, reduction, nucleophilic addition elimination, and certain named reactions. So we'll do all of these categories. In this particular video, we'll talk about oxidation reactions specifically. And here we'll start by using KMnO4 and potassium dichromate. Now alkaline or acidic potassium permanganate or acidified dichromate oxidize aldehydes to acids, while ketones are resistant towards this oxidation but do cleave with these reagents under vigorous conditions according to the Popov's rule, which we saw in alcohols. So please check out the video if you haven't. So aldehydes react with acidified or alkaline KMnO4 and they produce carboxylic acid. If it is alkaline, it will produce a carboxylate ion. If it is acidic, it will produce a carboxylic acid. While ketones, only under vigorous conditions, will react and they will cleave according to Popov's rule. And that rule said that the carbonyl carbon will go with that alkyl group which has less number of carbon atoms. So the cleavage occurs here. It converts this into acid and it converts this into acid, which is why you get 2-acetic acid. So here I'm going to show you a video of this particular reaction where an aldehyde and a ketone are reacted under normal conditions. This is oxidation of an aldehyde by KMnO4 solution. I'll be using a test tube containing aldehyde, which is to your right, and on the left test tube I have taken distilled water, which will act as a control. I add a few drops of KMnO4 to each. Then add a few drops of concentrated sulfuric acid as I am doing the oxidation in acidic medium. Now I place the test tubes in a hot water bath for a few minutes. You'll notice that the test tube with aldehyde has decolorized KMnO4 by reducing it, while the test tube with distilled water remains colored. Alright, so you saw the video now. Let's look at the next one, that's called the Tollen's reagent test. And it's also an oxidation reaction. Now Tollen's reagent contains diamine silver 1 ion, which is obtained through ammoniacal AgNO3 solution. So you add ammonia to AgNO3 solution, you will get diamine silver 1 ion. Now the Tollen's reagent oxidizes aldehydes to acid salt because it is basic medium, and they get reduced to silver in the form of a silver mirror. So basically what happens is, you have an aldehyde, you react it with the Tollen's reagent, which is basically this complex, diamine silver 1 ion, or you can call it ammoniacal silver nitrate. In the presence of hydroxide ion, the aldehyde will get oxidized to acid, and since the medium is basic, it will form the acid ion. The silver ion from this complex will be reduced to metallic silver, and you will have ammonia and water produced. And the silver will get, this is a colorless solution, the silver, which is going to be a gray precipitate, will get deposited on the walls of the test tube or the beaker in which you are doing the reaction. Now the Tollen's reagent oxidizes aldehydes to acid salt, and they get reduced to free silver in the form of silver mirror. Tollen's reagent is used in differentiating aldehydes from ketones because ketones do not react with them. Moreover, Tollen's reagent does not react with ketones, it doesn't react with alcohols, it doesn't react with carboxylic acids, amines, esters, ethers, hydrocarbons, aldehydes, non-aldehydic aromatic compounds. So the advantage of this reaction is that if you have a situation where you have an aldehyde and an alcohol, and you want to oxidize only the aldehyde part and not touch the alcohol part, Tollen's reagent is one of the best way to go, because it will only react with the aldehyde, will not affect the alcohol, whether even if it is primary or secondary. Now, remember Tollen's reagent was also used in terminal alkynes. It gave a white precipitate of silver salt with terminal alkynes, but that is not Tollen's test. If you remember, we used alkyne in hydrocarbons, we did this. If you use the same diamine silver 1, what will happen is this, with of course you have OH minus. Now this OH minus is going to remove this H, acidic H, and the silver salt of the alkyne is formed. So it is not giving you metallic silver, but it is reacting, and this is giving you a white PPT. So the Tollen's reagent does react with terminal alkynes, but doesn't give Tollen's test. The Tollen test is when silver is produced. Another advantage of this is that it does not touch the carbon double bond carbon. So unsaturated aldehydes can be converted to unsaturated acid using Tollen's reagent. So you have an unsaturated aldehyde here. Doesn't matter if it is conjugated or not. Tollen's reagent, and there you go, you get the acid ion and metallic silver. So now I'm going to show you a video of the Tollen's test. This is Tollen's test. This test is given by aldehydes and not by ketones. I have an aldehyde in this beaker that will be oxidized. It will therefore act as a reducing agent. It will reduce the Tollen's reagent that contains Ag plus ions, which in turn will be reduced to metallic silver. I will be doing the reaction in this big flask, wherein the silver will deposit on the inner walls of the beaker and create a mirror on the outside. First, I'll add the aldehyde. Then the Tollen's reagent. and then hydroxide ions that helps catalyze the reaction. I'll put the top on the flask and then shake the mixture for some time. And there you go. You can see the reflection on the flask. In the second part, I will reconvert the silver inside the flask with a reagent which has a higher reduction potential than silver ions. The silver will be reconverted back to silver ions. For this, I'll use nitrate ion, which will oxidize the silver back to silver ions. And now you can see all the silver oxidized from the beaker. So the next one is the Fehling's reagent test. This is also oxidation. Now aldehydes reduce Fehling solution to red cuprous oxide. Now Fehling's solution is made by mixing two solutions, Fehling's A and Fehling's B. Now Fehling's A is simply copper sulfate, aqueous solution of copper sulfate, which is deep blue. Rather it is blue, I would not call it deep blue, it's blue. The Fehling's B on the other hand is a colorless solution of aqueous potassium sodium tartrate, also known as the Rochelle salt, that is made strongly alkaline, commonly with NaOH. Typically, the L-tartrate salt is used. The copper-2 complex in Fehling solution is an oxidizing agent which will oxidize the aldehyde and itself will get reduced and the Cu2 plus will become Cu plus. So basically, this is the sodium-potassium tartrate. This is the copper sulfate that is added to it from Fehling's A in basic medium. And then you get the Fehling's reagent. So Fehling reagent is made up of Fehling's A and B. And this is deep blue. So what happens is that when you react an aldehyde with this using some a complex like this, in the presence of hydroxide ion, the aldehyde will become the acid ion as expected and reduce the copper ion to Cu2O, which is a reddish brown precipitate. And this is the Fehling's test. Now let's understand why can't we directly use copper sulfate, because ultimately it is the copper which is becoming Cu2O, right? So we cannot directly use CuSO4. It has to be in the form of a complex. The reason is, this is due to the fact that for the reduction of copper ion to copper plus, copper 2 plus to copper plus, hydroxide ions are required, okay? So now you'll ask, why don't we use copper sulfate with NaOH? Well, if the Cu2 plus is not in the form of a complex, then it will form CuOH twice, which is a pale blue precipitate. So what is happening is, if you were to use simply copper sulfate with ammonia or copper sulfate with NaOH, because you need OH minus for the reduction of Cu2 plus to Cu plus, instead of making the reaction happen, the Cu2 plus itself will become a precipitate of copper hydroxide, which is pale blue. So you don't want that. So you need to have the copper in the form of a complex. The second part is, moreover, the two Fehling's solutions have to be mixed just before the test and cannot be mixed and stored. So this is what we call as mixed, or the reagent is added in C2. So there is no Fehling solution available. You have to create the Fehling solution every time you want to use it. This is because the complex, for the complex to form hydroxide ions are required, right? So if you want to form the complex, you need hydroxide ions. On long standing, the complex would dissociate and again form copper hydroxide. So again, see the dilemma. The dilemma is, If you say, okay, I'm going to do the reaction after 2 hours and let me mix A and B right now and maybe keep it for some time, it doesn't work that way. You have to do it right just before the reaction. The reason is that even if you have a complex formation, that which also requires hydroxide ion, by the way, the complex would slowly dissociate over a period of time. And it again give you copper 2 plus ions. And again, this copper 2 plus ion will react with hydroxide to form copper hydroxide. So the result happens to be the same. So not only can we not simply use copper sulfate with NaOH, we cannot keep the Fehling solution prepared also. We have to make it just before the reaction. Now, aldehydes can also reduce Benedict solution, which is very similar to Fehling solution. Only thing is, instead of copper, instead of using the tartrate ion, we use copper citrate. The result is the same. You get Cu2O red PPT. You can also use what is called as a Barfoot test. So you can use Cu2 plus in the form of a Barfoot test, whereas this uses copper acetate. The ketones are not easily oxidized, thus they do not reduce Fehling solution or Tollen's reagent. But there's a specific ketone which does that, that is primary alpha hydroxy ketone. They're oxidized by both Tollen's and Fehling solution and also Benedict's and Barfoot solution. This is because the primary alpha hydroxy ketones enolize to form enediols, which tautomerize further to yield aldehydes. Now let me explain this. Now what I'm basically saying is that ketones don't react, okay? Only aldehydes do. So for aldehyde, you have this group, right? So let us take a ketone. Let us take acetone, for example. It's not going to give the test because it doesn't have an H. But if you have a primary alpha hydroxy ketone, something like this. Can you understand? This is a primary carbon, primary, and this is also alpha carbon, primary alpha hydroxy ketone. Now, how does it do that? Well, what it does is it tautomerizes. This C double bond O will tautomerize with the H here. It will give you this tautomer. Is it not en diol? Now, these two can tautomerize. So you have a COH here and an H here, and then you have a C double bond O and you have an H. Can you see this H has transferred here and the double bond is transferred here? Isn't this now an aldehyde? So primary alpha hydroxy ketones can give this reaction, but not normal ketones. And the reason you need primary alpha hydroxy is because obviously you need alpha hydroxy. Only then it can tautomerize twice. The reason it has to be primary is because if you have any more carbon attached to that carbon, if it is not primary, then the end result of that tautomerization will also be ketone. To make sure that that end result is an aldehyde, it has to be primary. But having said that, there has been a question in JEE Advanced where they simply said alpha hydroxy ketones, give the test. Now many students wrote, no, it has to be primary alpha hydroxy ketone. But the answer of IT was, no, it is alpha hydroxy ketone. So technically it is not true. It is primary alpha hydroxy ketone. But just to provide you this information, there has been once a question where they said it is simply alpha hydroxy ketone. So but they might have been meaning primary, but they didn't specify it. And in an exam, you have to specify everything. So barring that question, technically it has to be a primary alpha hydroxy ketone. Okay. So aromatic aldehydes do not give the Fehling's test, as the presence of high concentration of hydroxide ions on aldehyde without alpha H causes Cannizzaro reaction. And this is again a problem. Benzaldehyde won't give this reaction because in benzaldehyde, I mean, technically it can, but the problem is it undergoes another reaction called Cannizzaro reaction, which we'll do later during the name reactions. So in the presence of hydroxide ion, benzaldehyde will show Cannizzaro reaction. So it will not give a positive Tollen's test. Formic acid is also reduces Fehling's, Benedict's, Barfoot's and Tollen's reagent. This is because formic acid has a H atom attached to the carbonyl carbon to behave similar to aldehydes. It will get oxidized to H2CO3. So basically formic acid is what? This is formic acid. This looks similar to an aldehyde and therefore it tends to give this reaction. And to show you which gives which test, I've made a table here. And basically I'm going to compare Fehlings and Tollens. So this is the compound, this is the Fehlings, and this is the Tollens. And glucose and fructose both give. Primary alpha hydroxyketones, this gives and this gives also. Glyoxal doesn't give the Fehlings test, gives this. What is glyoxal? Glyoxal is this. This is glyoxal. So it doesn't give the Fehlings test but gives the Tollens test. Aromatic aldehydes, we said it doesn't give the Fehlings test, gives the Tollens test. And formic acid gives both. Glyoxylic acid won't give the Fehlings but it will give the Tollens. Glyoxylic acid is this. And pyruvaldehyde will give both. So what is pyruvaldehyde? Well, it is CHO and a COCH. So this will also give, and that's pretty logical here. Okay. So now I'm going to show you a video of the Fehlings test. This is an oxidation reaction called the Fehlings test. We will do the test by reacting both aldehydes and ketones separately. First, we make the Fehlings reagent. It uses Fehlings A solution, which is an aqueous solution of blue copper sulfate. To this, we add Fehlings B solution, which is a solution of potassium hydroxide mixed with sodium potassium tartrate. This gives a deep blue colored Fehlings reagent. This solution is heated on a hot plate. To the solution on the left, a ketone is added, while to the one on the right, an aldehyde is added. The solution on the left shows no color change, while the one on the right shows the formation of a reddish brown precipitate of copper 1 oxide. The next is the Schiff's reagent test, and this also is an oxidation reaction. A solution of para-rosa aniline hydrochloride is magenta or pink in color. Okay. Now the pink color of this reagent is removed or discharged by adding SO2. This resulting solution, colorless, is called the Schiff's reagent. Now when aldehydes react with this decolorized solution, the pink color of the solution is restored, though the two pink colored compounds are different. And this is called the Schiff's test. So let me explain. You don't have to remember the reaction or anything because it's very complicated. This is para-rosa aniline hydrochloride and this is pink. When you treat it with SO2, it will oxidize this and also form amide with the NH2 and form a compound like this. And this is colorless. This is Schiff's reagent. Now when this reagent further reacts with aldehyde, aldehyde gets oxidized and this thing gets reduced and it forms this. And can you see this is nowhere similar to what this initial one was? But this also happens to be pink. So this is Schiff's test, given by aldehydes, not given by ketones. So let's see a video on this. This is an oxidation reaction called the Schiff's test. Aldehydes react while ketones don't. We will do the test in 3 parts. First, for those aldehydes that are soluble in water and can react with the Schiff's reagent easily. Then for water insoluble aldehydes. And then for a twist, to test whether we have carbohydrates in our skin. In the first part, we take formaldehyde in 1 test tube. while we take acetone in the other. We put distilled water in both to dissolve them and dilute the solution approximately 30 times. We add the Schiff's reagent to both. As can be seen, the formaldehyde solution turns pink or magenta quite quickly, while the acetone solution does not. In the second part, we test for aldehydes that are insoluble in water. We will take benzaldehyde. We will try to use the pure form and use a solution of it in ethanol. We should get a positive test in the ethanol solution, but not in the pure form. As in the pure form, it won't be able to react with the Schiff's reagent. But to do this, we need to also test whether ethanol gives a positive test or not. So we take 3 test tubes. In the middle and the right one, we add benzaldehyde. Then, in the left and the right test tubes, we will add ethanol. In the right test tube, it will act as a solvent, and in the left, it will act as our control. Then we add the Schiff's reagent to all. You can notice that the right solution starts turning pink immediately, which is not the case with the middle and the left test tubes. Now coming to the interesting part, let's add a few drops of Schiff's reagent to a finger. It is not toxic, by the way. It takes up to 10 minutes for the test to give results. And now you can see the finger has become colored pink. It's not easy to wash it off though. The next one is selenium dioxide oxidation or the Rayleigh reaction. Now, aldehydes and ketones with a methyl or methylene group adjacent to the carbonyl group are oxidized by selenium dioxide in acetic acid at room temperature to a dicarbonyl compound. So, what I'm basically saying is, you have a carbonyl compound. Now, it should have a CH3 or a CH2 attached to it. So, when you have a selenium dioxide in the presence of acetic acid, this CH3 or the CH2 will also be oxidized to a carbonyl compound. So here I have shown the left carbon getting oxidized. It has become a carbonyl compound, and since it is primary, it forms an aldehyde. It could be, however, a ketone also. So if I start with this, well, both will become C double bond O now, glyoxal. And as I said, you can even have a CH2. It will give you 2 of them. First, the right one can get, and secondly, the left one can get. Sorry, I think the first one, the left one got, the first one, left one got oxidized. The second one, the right one got oxidized. And the major is the right one, and the left one is the minor. And we'll see why. Well, the simple answer is that the reaction occurs through the enol form. The actual reagent of the reaction is selenous acid, which is H2SCO3, and the reaction proceeds via the enol form of the carbonyl compound. The mechanism is like this. You have the carbonyl compound. Now in this case, as you can see, there are two enols possible. One enol with this, one enol with this. And you will notice that this enol is more stable because of hyperconjugation. So the one which forms a better enol is the one that will get oxidized. So first of all, it will tautomerize and form the enol. This is H2SCO3, and the reaction goes like this. The lone pair of O attacks the H. This goes in between these two. The pi bond comes between C and O, and the pi bond goes to selenium, and then this goes to OH to remove water, and you get something like this. The next step, the OH attacks the H. This goes here, and then this goes as water. You get selenium precipitate, and you get a carbonyl part. The next oxidation is called the Baeyer-Villiger oxidation. Very interesting one. In this reaction, an oxygen atom is inserted between the carbonyl group and the group attached to the carbonyl group that has a higher migrating aptitude. Basically, what this does is it converts a ketone into an ester in one step. Now, aldehyde to ester is possible. First convert that into acid, then make it react with an alcohol. But a ketone to ester, ketones are very difficult to oxidize. But this is a single step reaction where, not a single step reaction as such, but a single reaction in which the ketone directly forms an ester. So the O gets inserted between the carbonyl carbon and one of the alkyl or aryl groups attached. Now to which one it gets attached depends on the migrating aptitude of the group. Higher the migrating aptitude, more is the insertion of O towards that alkyl group. The reagent used is a peroxy acid. You can even use H2O2BF3 or H2O2 base. Now, aldehydes are converted to acids while ketones are converted to esters. Now, we don't do the reaction for aldehydes firstly because aldehydes can be converted to acid anyway. You can have KMnO4 and all the reactions that we saw right now. So, you can have all those reactions converting an aldehyde into an acid. Now, since aldehydes can be converted to acids by other reagents too, this reaction is more important for ketones. And this is the only reaction that can convert them into ester by one reaction. So basically, you have this, and one of the peroxy acid, if you remember, is MCPBA, metachloroperbenzoic acid, which we saw in the case of ethers, cyclic ethers. Check that out. Now, out of CH3 and pH, which one do you think has a higher migrating aptitude? Obviously, pH. So you're going to get O inserted between the carbon and the pH. This is how you do the reaction. Now, of course, if you have an aldehyde, the H has higher migrating aptitude, so it will become acid. But we don't need this. It can be converted into acid anyway. Let's look at this one. What do you think will be the product? Pause the video. Now, since both sides are the same, O can get inserted anywhere, but since it's a ring, you'll get a cyclic ester, a lactone. What about this one? Pause, make and play. Obviously, the right carbon, this carbon is has more migrating aptitude because it is a tertiary carbon, and you will find the O getting inserted here. But the migrating aptitude of the groups here is slightly different from that of a carbocation rearrangement. It goes like this. Hydrogen is best, then tertiary, then secondary. Secondary and phenyl is almost same, and then primary, and then CH3. And this is different from the migrating aptitude that you find in carbocation rearrangement. The mechanism is pretty interesting. You need to know the mechanism sometimes. So this is the acid. The lone pair of O captures this H. A minus is released and you get this. Then this lone pair attacks because you need to know which O of the peroxy acid is attaching. So remember, it is the OHO that is attached. And then the A minus will pick up this proton. This will go here. You'll get this. Now the O bond is pretty much unstable. So this picks up the H plus. Again, A minus is released. You get this. And this goes off. Therefore, this bond goes off and the O becomes plus. which is not good. So one of the group migrates, the one with the higher migrating aptitude, and you'll get a C plus formed temporarily, and the A minus will attack this and convert this, and you get this. So remember, it is this O that is getting inserted. So if this was O18, you will get O18 here. But if this were O18, you will not get any O18 in the ester. So that is the, just two more examples. Try this, pause the video, make the product and then play it back. Obviously, ethyl has higher migrating aptitude. I think one can clearly see the left one has more migrating aptitude. That is the end of this part 4. So with that, we come to the end of the first chemical property of aldehyde and ketone, that was oxidation. And as I had said earlier, the reactions of aldehyde and ketones are being done together to understand what do aldehyde gives, what do ketones give, and when does aldehyde react, ketone doesn't, when does ketone react, aldehyde doesn't. Where is it important for the ketone to react, not for the aldehyde, like we saw in the Baeyer-Villiger oxidation. So we will do the reactions combined. So that was oxidation. The next one will be reduction. Till then, have a great and productive day. Goodbye and thank you for watching this.